Okay, today we're going to go over our fourth quiz from this semester. This quiz was from Chapter 4 and specifically focusing on redox reactions and concepts that surround the idea of redox reactions. So oxidation states is a big key as we go through this quiz here. Now, when we talk about oxidation states, we have to know our rules, right? And that's the big secret. Well, it's not really a secret, but that's the trick that we have to use behind the scenes here, right? We have to know the rules that are involved with oxidation states, or we can't really answer any of these problems. Because if you read problem number 1 here, it says determine the oxidation state for each element, right? So we have to know how to get the oxidation state. Remember, oxidation number, right? It might be another way of saying that, right? Oxidation state or oxidation number for each element in the following compound. Okay, so remember, just as we always did in class, just as all the examples in the books and all the examples you might look at, oxidation state is something that is listed per atom, per element that's in there, right? Per atom, per component, right? Per unit that's in a formula, right? So for each of the examples that we have here, we're going to have to determine the oxidation state for an individual atom, okay? For an individual atom in these problems. Okay, so like I said, we have to know our rules. Now I'm going to be using the rules that we covered in class. If you look it up in the book or you do a Google search or whatever it is, you might come up with some slightly different rules about how to determine oxidation state, right? But whatever you want to do, whatever resource you want to use, you have to know a list of rules. Okay, because the way we're going to solve all these problems is we have to have a known, okay, oxidation state, right? So we have to look in the formula, right? We have to look in the compound that we're examining, and we have to identify a known oxidation state. That is, one of the atoms or one of the elements that are in there, all right, is going to have a defined oxidation state based off our rules. And we use our known oxidation state to determine our unknowns. Okay, so we're going to have to identify knowns, and then we're going to use our knowns to identify our unknowns. Okay, so I'm going to switch over to the rules just as a quick recap. Okay, so where was it? Should be here. Yeah, there it is. Okay. Ooh, I need to zoom in. All right, let's start here. Right, this is what I'm talking about with the rules. Okay, I'm not going to read this through in this. Read this through for this recording here, right? You guys have it. All I'm going to do is say there's two very important things to pay attention to, right? The sum of all oxidation states of all atoms is equal to the compound charge, okay? And here's what I mean for my knowns. Oxidation states are often constant for certain elements, aka oxidation states are known for certain elements. So these two are core important ideas which I'm going to be referencing over and over and over and over again, okay? So let's look at the constant or known oxidation states. What are the rules for that? Well, here they are. Okay, fluorine's -1. There's no exceptions. Oxygen's -2, with the exceptions being a peroxide or the halogen oxides. Halogens tend to be -1. We talked about the interhalogen idea here, right? We talked about that during lecture. Hydrogen is +1. Group 1A metals are 1+, and group 2A metals are 2+, okay? So these are the known rules that we're going to use, okay? So when we're starting out a problem by assigning oxidation state, we have to know these rules here, right? There is no real mystery or trick about it until we learn something later on in the semester, right? Well, there's a way that we can kind of work a way around this, but in general, these rules aren't that bad, right? Fluorine, oxygen, or halogens, or group 1A or group 2A in hydrogen, right? There's not too much to memorize here, okay? So know these rules. Okay, I'm going to switch back to my quiz. Here it is. All right, so hopefully, you can rewind, pause, make sure you have a copy of those rules down, because here's what we're going to use. All right, so I'm identifying the oxidation state. I look at my rules. My rules do not cover anything with sulfur, okay? So my sulfur is my unknown. So I have to figure out what sulfur is. But my rules do say something about hydrogen. It says that hydrogen is typically 1 plus. Okay. So each hydrogen, right, each element in this case, right, each atom in this case of hydrogen has a 1 plus. But there's 2 of them, right? So if 2, let me just redo this real quick. So if 2 times 1 plus, right? So a plus 2 coming from my knowns. If you take a look at the rules, it says that the sum of the oxidation states has to be equal to the compound charge. What is the compound charge here? Right? What is the compound charge of H2S? Well, there isn't a charge, right? If there was, I would have to specify it. There is no charge, right? So the overall charge is 0. That means I have to cancel out that plus 2 with a minus 2 for my unknowns. Got it? Everything has to add up to be equal to 0. It has to be that neutral charge on this compound. That's 0. Well, I only have 1 sulfur, and everything has to add up to be equal to 0, so each sulfur here has a minus 2 charge. Okay? So, in the interest of keeping things organized, what I'm going to do is write my answers here, right? So hydrogen plus 1, sulfur minus 2, okay? Now I'm just going to repeat the same thing. I'm just going to erase this stuff, and we're going to move on to problem B, right? Guess how we're going to solve problem B? We're going to identify our knowns, and then we're going to go to our unknowns. We're looking at problem B here. There's no rule about sulfur, okay? But there is a rule about chlorine. Chlorine is a halogen, okay? It says in our rules that halogens are minus 1 unless there's an interhalogen, right? Well, there is no interhalogen issue here, right? So chlorine is minus 1. There's a total of 2 chlorines. Each one has a minus 1 charge, so minus 2 coming from my knowns. This is another neutral compound, so my unknowns have to be equal to plus 2. Now, we just have a sulfur, right? So sulfur is a plus 2 in this case. Right? There's only 1 sulfur atom, right? There's only 1 sulfur atom, so it has to have that plus 2 charge to balance out the total minus 2 from the 2 1 minus chlorines. All right. Just erasing to move on to problem C. Well, problem C was actually one we worked in class, right? It comes from the notes. But that's okay, right? Because we're going to approach it the exact same way, all right? We identify our knowns based off of the rules. Our rules do not cover phosphorus, but it does cover oxygen. Our rules say that oxygen is minus 2 unless it is a peroxide or a metal oxide, excuse me, unless it's a peroxide or our halogen oxide, okay? But there is no halogens in number C, right? And this is not a peroxide, right? So we don't have any of our exceptions. We have an oxygen that's minus 2. There's 5 of them. So 5, right, times the negative 2, there's a total of negative 10. There's a total of negative 10 on this compound coming from the 5 oxygens, which means our unknowns have to be equal to plus 10. But be careful, right, because we have, right, phosphorus is our unknown, but there's 2 of them, right? So that plus 10 charge is spread out, right? It's handled by that phosphorus, the 2 of them, right? So plus 10 divided by 2, so a plus 5, right? Plus 5 for phosphorus, minus 2 for the oxygens. Okay. D. So problem D is a little bit trickier, right? It's a little bit tricky because we're dealing with a compound that has 3 elements in it, right? But guess how we're going to solve it? The exact same way, right? We got to identify our knowns, and then we identify our unknowns. So, starting from the left, K, potassium. Well, potassium's a group 1A metal. And that's good, because we know that group 1A metals are a known. They are always going to be 1 plus. I cannot think of any exceptions to this, right? There are no exceptions that I know of. If you do know one, right, send me a note and I'll fix this, right? But I cannot think of an example where potassium is not a +1, right? The obvious exception being in its elemental form, right? But this isn't an elemental form, right? So potassium, 1 plus charge. But if you look, right, we also have oxygen in here. And oxygen is also a known, right? Oxygen is 2 minus. So we've already got 2/3 of this done. That only leaves our unknown as our chromium, right? So we got to just play the balancing game here, right? There's 2 potassiums, each one is 1 plus. There's 7 oxygens, each one is 2 minus, right? So if we add this all up, right, we have a 2 plus and a 14 minus, right? So a total of minus 12 coming from our knowns. That means our unknowns have to be equal to plus 12. But be careful, right, because we got 2 chromiums. So plus 12 divided by 2, so each one is plus 6. Right? So I'll try and stick with the coloring here. Plus 6. See, red for potassium, plus 1. Oxygen, and purple, 2 minus. Okay? Use your rules to determine your knowns. Use your knowns to determine your unknowns. That's how it's done. Okay, question 2. 2 parts to it. It says determine the reducing agent. It'll ask us to figure out how many electrons are transferred. Okay, so we have to know what the definition of a reducing agent is. You can kind of talk yourself through it. A reducing agent means it is an agent of reducing. It is an agent that causes reduction. Reduction is a gain of electrons, but if you're the agent, that means you cause the gain of electrons, right? If you're an agent, you cause something to happen. A reducing agent causes reduction to happen. Reduction is a gain. That means you lose electrons. Oof. Right? That's kind of a up and down, back and forth, kind of logical shuffle there, right? So if you want to pause and back up, right? A reducing agent means you're an agent of reduction. Reduction is a gain of electrons. If you're an agent that causes reduction, which is a gain, that means you have to lose electrons. Reducing agents lose electrons. They get oxidized. And that's what I remember. Reducing agents lose electrons. It gets oxidized. Okay, so I just remember that set right there. Reducing agents lose electrons. It gets oxidized. Okay, so we know that in question 2 we have a redox reaction because otherwise we don't really have a reducing agent, right? Now, how do we go through and identify a reducing agent? Well, how do we go through and identify an oxidizing agent? How do we go through and identify something that's reduced? How do we go through and identify something that's oxidized? The same answer for any of those is you have to assign your oxidation states. Okay? You have to assign oxidation states in this reaction. Guess how you assign oxidation states in this reaction? That's right. You identify your knowns, and you use your knowns to identify your unknowns. Okay? Now, I'm not going to go through the same rigmarole for everything here in question 2 as I did in question 1, right? But I do want to talk about the first thing that we encounter. right? Because this might be something that you encounter on an exam or another quiz or whatever it might be, or walking down the street. I'm sure that's what happens, right? Okay, so we see a problem. We have to identify oxidation states. We pull out our list of knowns. We look, okay, there's nothing in our list about lead. Okay, there's nothing in our list about sulfur. Right? Now what do we do? Well, now we've got to go back and actually think a little bit, right? Now we can't just fall back onto a memorized list. So what do we know? Well, PBS, lead 2 sulfide here, right? Lead 2 sulfide is an ionic compound, right? Lead 2 sulfide is an ionic compound. We do know in our rules, right, that the charge of ions, the charge of individual ions, is equal to its oxidation state. And if you want to back up to look at your rules, one of the rules says that the charge of individual ions is equal to its oxidation state. Now, if I had asked you for the name of this compound, you should be able to go through and name it. Right? We know that Pb is lead. It is a variant metal, so we would use the sulfur to determine the charge on the lead. So the question is, in this case, how do we know what the charges are in the individual species? Well, we got to go look at our periodic table, right? So I'm going to scroll down, periodic table. Here's my buddy sulfur, right? Now, there's a rhyme and a reason for the rules that we have for oxidation states. There's a rhyme and a reason why things exist in the charges that they do. Okay? Now, we talked about this a bit, and at the moment, right, with the current way that we're going through Gen Chem, we explained it by saying there's something called the Octet Rule, which says that atoms want to get to the closest count of 8 with electrons. And what we mean by that is they want to get to the closest noble gas. Okay? So, if we're sulfur, when we want to get to the closest noble gas, we go 1, 2, right? That means to get to the closest noble gas, I would have to add 2 electrons. So sulfur typically, okay, in an ionic compound, has a -2 charge. Okay? And that's what we will see in the particular example that we're looking at. But I want to make a point here, right? Because if you take a look at the other examples that we've done and the stuff in the book, sulfur isn't always, excuse me, sulfur is not always a -2 charge. If it was always a -2 charge, then it would be in our list of rules, but it's not. It's not. So what else can sulfur be? Well, instead of walking forward, sulfur can walk backwards. 2, 3, oops, that kind of missed. Let me go back and fix this. 3, 4, all right, all the way here, all right. Okay, so it can walk backwards to get to a noble gas. So 1, 2, 3, 4, 5, 6. If I'm following my green arrows, it takes 6 steps to get to neon, all right? So sulfur can take 6 steps backwards or 2 steps forward. So it can exist in theory, anywhere from 2- to 6+. Okay, so sulfur, for its oxidation states, is going to exist anywhere from 2- to 6+. It doesn't mean that it can only be 2- or only 6+. Anywhere in between there is technically viable. Okay? So in this case, it is the anion, right? Because here's our buddy lead down here, right? Lead is a metal, right? And we've talked about how metals and nonmetals bond in ionic species. And we know that sulfur is going to be the anion. It's going to be 2- in this case. So it's important to recognize what the limits are on oxidation states. And it's based off of where in the periodic table things exist. So it's somewhat based off of ionic charges, although there's something else working behind the scenes, which we'll talk about a little bit later in the semester. Okay? Sulfur in this case is a 2-. So let me scroll back up now that we've identified that. Right? Known, whoops, I meant to do that, right? Known sulfur 2-, or unknown lead 2 plus. Okay. Now I'm just going to go through and knock out the rest of these very quickly, right? Hydrogen 1 plus. And I'm going to put oxygen 1 minus in red also. Say, hey, wait a minute. No. Oxygen is always 2 minus. Yep, except when it's in a peroxide. Take a look at your rules, right? Here we've got hydrogen peroxide. How am I supposed to know that? Well, if you're in my class, right, I'll tell you guys when you have a peroxide until we can figure it out for ourselves, which we don't know how to do yet. Okay, we need to know how to draw a Lewis structure, then we can know about peroxides. Okay, but at the moment, I told you guys that this was hydrogen peroxide. It's also explicitly written in the rules that I give you guys. Right, if you back up the video, right, you guys will see that hydrogen peroxide is explicitly written in the rules. Okay, so here we have oxygen 1 minus, hydrogen 1 plus. These are both knowns. Okay, moving on to the next one. Lead 2 plus in this case, right? Sulfur 6 plus. Oxygen, where is it? Here it is. Oxygen 2 minus. Okay. If you don't know how I got these values, pause this, walk through the individual steps, please. This is going to be on the exams, I promise you. Okay. All right, so there's all my oxidation states. There's all my oxidation states. Well, we still haven't answered the question, right? Because we need to figure out the reducing agent. Now we have to look for a reducing agent, remember, something that loses electrons that gets oxidized. So what loses electrons? Well, let's go through individually. Lead starts at 2 plus, it ends at 2 plus. Sulfur starts at 2 minus. Let me change colors here. I think you guys might have already seen what's going on. Sulfur starts at 2 minus, ends at 6 plus. Okay. Hydrogen starts at 1 plus, ends at 1 plus. Oxygen starts at 1 minus and ends at 2 minus. Okay, so lead doesn't change, so it's not a reducing agent. Hydrogen doesn't change, it's not a reducing agent. So we've got two things that change, right, in the purple and in the green. Sulfur goes from a 2 minus. Sulfur goes from a 2 minus all the way to a 6 plus. What is happening to the sulfur? It starts at 2 minus, it goes to a 6 plus. What's my change in electrons here? Well, my change in electrons is 8, right? How do I get from 2 minus to 6 plus? Well, I have to lose 8 electrons. Right? How do I go from minus 2 to plus 6? I lose 8 electrons. Okay, so we kind of answered the second part here, right? And if we take a look up here real quick, reducing agents lose electrons, it gets oxidized. So the sulfur is our reducing agent in this case, because it lost 8 electrons. But let's pause and make a quick point. If something loses 8 electrons, what does that mean? Right? Well, if something loses it, something has to gain. So what's gaining electrons in this case? Well, the oxygen is. Right? Oxygen goes from 1 minus, and it ends up at 2 minus. Right? So we have a change in electrons of 1. Hey, wait a minute. Right? Everything has to balance. If sulfur loses 8 electrons, how come oxygen only gains 1 electron? Well, how many oxygens are there? Take a look right here, right? There's 4 times O2, right? So 4 times 2, 8 total electrons. And you can count it up, right? There's 8 electrons on this side here also. 4 there and 4 here also. So 8 electrons, 8 oxygens on both sides, each one gaining an electron. Everything has to balance. Okay? So the reducing agent is sulfur, right? Reducing agent is sulfur, and How many electrons are transferred? 8. All right, last question. Define oxidation and reduction. Oxidation, we can simply say it is a loss of electrons, right? And reduction is a gain of electrons. There it is. Okay, I'm going to zoom out so you guys can see it all. If you have any questions, please come see me or send me an email or whatever it might be.